You have tied your shoelaces. You have braided your hair. You have watched a sailor tie a knot in a rope, or a weaver interlace threads to create a fabric. Braiding is one of the oldest and most fundamental human actions. It is the art of taking strands and winding them around each other, creating a structure that is stronger, more complex, and more beautiful than the individual threads alone. Braids are everywhere, in our clothing, our jewelry, our mathematics, and, as it turns out, in the deepest structure of the universe itself. But here is the thing that will blow your mind. The strands in a braid do not have to be physical threads. They can be particles. They can be quantum states. They can be the swirling, ghostly waves of matter that exist at temperatures colder than the vacuum of deep space. And the act of braiding these quantum strands is not just a mathematical curiosity. It is the key to building the most powerful computers the world has ever seen. It is the key to topological quantum computing, a technology that promises to be immune to errors, incredibly robust, and capable of solving problems that would take our most powerful supercomputers billions of years. For years, the idea of braiding quantum particles was a beautiful theory. It was a concept that existed on blackboards and in the minds of physicists. But actually doing it, actually taking quantum matter and forcing it to braid, that was a different story. The theoretical proposals were elegant, but they required a process called adiabatic evolution. This is a fancy way of saying that you have to move the particles incredibly slowly, so slowly that the quantum state never has a chance to jump to a different energy level. It is like trying to thread a needle while moving your hand at a glacial pace. It works, but it is agonizingly slow. And in the quantum world, slow is a problem because quantum states are fragile. They decohere, they fall apart, they lose their information to the environment. The slower you go, the more time there is for the quantum state to decay. It was a catch-22. To braid, you had to be slow. But to survive, you had to be fast. That was the state of the field until July 3, 2026. On that day, a team of researchers from Shaanxi University in China and the Beijing Academy of Quantum Information Sciences published a paper in the journal Nature Communications that changed everything. They had done the impossible. They had performed non-adiabatic, non-abelian braiding operations using quantum matter waves. They had braided quantum strands quickly, efficiently, and without losing the quantum information. They had opened a new paradigm for quantum state manipulation. Let me explain what they did and why it matters. To do that, we have to talk about one of the strangest states of matter in the universe, the Bose-Einstein condensate. A Bose-Einstein condensate is often called the fifth state of matter, distinct from solids, liquids, gases, and plasmas. It is created when you cool a dilute gas of bosons, particles that have an integer spin, to temperatures just a fraction of a degree above absolute zero. At these unimaginably cold temperatures, the particles lose their individual identities. They stop behaving like separate marbles bouncing around a box and start behaving like a single coherent wave. They condense into a single quantum state, a superfluid that flows without friction. It is the closest thing we have to a quantum fluid, a material that is governed entirely by the strange rules of quantum mechanics. The Chinese team took a Bose-Einstein condensate and used it to simulate the braiding of quantum strands. How did they do it? They encoded the strands of the braid not as physical threads, but as momentum states. In quantum mechanics, a particle does not have a single, definite momentum. It exists in a superposition of many momenta, a spread of possibilities. The team manipulated these momentum states using laser pulses to create a series of operations that mimic the act of braiding. It is like using a complex set of mirrors to guide a beam of light along a twisting path. The light is not physically woven, but its path traces out the same pattern as a braid. But here is where it gets really interesting. They did not just perform any braiding, they performed non-abelian braiding. Now, I need to explain what abelian and non-abelian mean. These terms come from mathematics, specifically from group theory. An abelian group is one where the order of operations does not matter. If you have two operations, A and B, and you do A then B, you get the same result as doing B then A. Addition is abelian. 2 plus 3 is the same as 3 plus 2. Multiplication is abelian. 2 times 3 is the same as 3 times 2. But not all operations are abelian. Think about rotating a Rubik's Cube. If you rotate the top face, then the right face, you get a different result than if you rotate the right face, then the top face. The order matters. Rotation is non-abelian. Non-abelian braiding is the quantum version of this. Imagine you have two particles, and you braid them around each other. You take particle A, you move it around particle B, and you bring it back to its starting position. In an abelian system, the quantum state of the particles would be multiplied by a simple phase factor. It would be like adding a constant to a number. The result would be the same regardless of the order of the braids. But in a non-abelian system, braiding the particles changes the quantum state in a more complex way. The order of the braids matters. If you braid A around B, then B around A, you get a different result than if you did the braids in the opposite order. Why is this important? Because non-abelian braiding is the foundation of topological quantum computing. In a topological quantum computer, information is stored not in the state of individual particles, but in the topology of the braids. The quantum bits, or qubits, are not particles. They are the patterns of the braids. And here is the beautiful part. Topological properties are incredibly robust. If you have a knot in a piece of string, you can jiggle the string, you can shake it, you can even stretch it, and the knot remains. The knot is a topological property. It is not affected by small perturbations. The same is true for braids. If you store information in the braiding pattern of quantum particles, that information is protected from errors. It is immune to the noise and decoherence that plague other types of quantum computers. Topological quantum computing is the holy grail of the field. But there has always been a problem. Non-abelian braiding is hard to do. The theoretical proposals required adiabatic evolution, which, as I mentioned, is incredibly slow. The Chinese team solved this problem by using a technique called non-adiabatic holonomic quantum computation. This is a mouthful, but the basic idea is simple. Instead of moving the particles slowly, they used a series of carefully timed laser pulses to guide the quantum state along a path that mimics the braid. The pulses are fast, they are non-adiabatic, but they are also precise. They ensure that the quantum state follows the correct path without losing coherence. The team verified their success by showing that different sequences of operations, applied to the same initial momentum state, yielded distinct outcomes. This is the signature of non-abelian behavior. The order of the operations mattered. And then they did something even more impressive. They showed that these operations could be used to prepare, transfer, and distribute momentum quantum superposition states. In other words, they were not just braiding for the sake of braiding. They were using the braids to do useful quantum information processing. They were creating superpositions, which are the raw material of quantum computing. They were transferring quantum states from one place to another. They were distributing entanglement across their system. They were building the basic operations of a quantum computer. Now, let me take a step back and connect this to the grand tradition of physics. Richard Feynman was a man who was obsessed with the idea that the universe is a vast, interconnected web of quantum states. He believed that the best way to understand the quantum world was to play with it, to build models, to simulate it. He famously proposed the idea of a quantum computer, a machine that could simulate quantum systems more efficiently than any classical computer. He would have been absolutely captivated by this discovery. Here we have a team of researchers who have taken a Bose-Einstein condensate and used it to simulate non-abelian braiding. They are not just studying the quantum world. They are building it. They are creating new quantum states that have never existed before. They are weaving the fabric of reality. The implications of this work are staggering. The researchers have opened a fast, non-adiabatic paradigm for non-abelian geometric manipulation of both classical and quantum waves. This is not just a scientific breakthrough. It is a technological roadmap. It shows us how to build topological quantum computers that are fast, robust, and scalable. It brings non-abelian braiding operations into a regime applicable to quantum state manipulation. It takes the concept of braiding from the realm of theory to the realm of engineering. And let me remind you of the timeline. This paper was published on July 3, 2026. This is not old news. This is happening right now. We are living in a golden age of discovery, a time when the boundaries between the possible and the impossible are being redrawn on a daily basis. The researchers at Hanqing University have not just made a small incremental advance. They have opened a new frontier. They have shown us that non-abelian braiding can be done quickly and efficiently. They have given us the tools to build the quantum computers of the future. So the next time you tie your shoelaces or braid your hair, think about the quantum braids. Think about the particles that are swirling and twisting in a Bose-Einstein condensate, their momentum states woven together in a pattern that encodes information. Think about the researchers who are learning to control these patterns, to use them to compute, to simulate, to explore the deepest mysteries of the universe. And think about the fact that you are living in a time when the impossible is becoming possible. The braids of the quantum world are no longer just a mathematical abstraction. They are a reality. They are the future. This is Feynman's Curiosity Lab. Stay curious. Keep asking why. And remember that the universe is not just something to be observed. It is something to be woven. And we are just learning how to braid.